So we'll get into that here. Let me screen share here.
As a matter of fact, if any Globey or any counter argument wants to put forth a paper that says perspective is perfectly Euclidean, I'd like to take a look at that. Right? There are no papers that say that. Only cartoons in your globe math says that. There are no actual academic scientific papers putting forth perspective perfectly explained Euclidean. So, just saying, if you find them, holler.
Yeah, it's really interesting because one of the main arguments put forward in all these papers is like a very simple introduction to the subject is how parallel lines are not supposed to converge if things are Euclidean. Well, there are these things called railroad tracks, and we know spatially they're parallel at all times, but visually we see them converging. That is a very simple, and like we'll hear people argue against that, but there's no answer for it. It's literally a violation of Euclidean geometry applied to optics, and it's the segue into people coming up with things like hyperbolic visual space to describe optics. So, yeah, we'll get into all that. So here is the presentation here. So this is the history of that. We're going to lay out the concepts before we get into it, though. And
Whoa! Look at you, dude! An artsy creator. All of a sudden,
dude, I can't resist. I can't resist.
That is wild.
Canva's too powerful, boys. All right. So that's where the bulk of the budget went. Also, I will be wait. Also, I will be using a penny later.
I have a real life prop or whatever.
Yeah, remind me to do the penny thing later. Don't let me forget. Okay. So to lay out some definitions here, this is from the field of psychophysics, which is basically understanding how we perceive reality. That's a real brief way to say what it is. And so the study of the deviation from the spatial field versus how we perceive it optically, how we interpret reality, how these tests that we're going to be going over can be influenced by suggestion, in fact. So there's a lot going on when we get into optics. So the field of study is psychophysics, and that is where we're going to start drawing our definitions for the spatial field here. So this is from Bloomberg. Started with Bloomberg. Okay. So Bloomberg talks about, how you perceive things in terms of color, brightness, that sort of thing. But one important thing to note is that all objects have a definite geometric form and a definite localization in three-dimensional space. When we talk about the spatial field, we're talking about where something resides in three-dimensional space, where it actually is, not where it appears to be, not where you see it with your eyes, but where the actual, if you were to get out a ruler and measure it from you to said object, what would be that physical distance? What would be that actual height? Where does it physically exist in the spatial field? So the spatial field would be, you can kind of think of that as actual reality, and then the visual field would be your perception of that, and we'll get into the deviations from the spatial to the visual, but that's from Carl Lumberg in 1947. This is from another paper on the subject where they talk about getting into the history of it. This, so going back to the 1800s, right? This isn't a concept that is recently invented or some ad hoc thing that we're putting forward, to explain things, but this is like an overlooked subject that's really not well explained and kind of understudied. But anyway, we'll continue on with the definitions here. So the spatial field again. So in the representations, in a presentation held in the 1870s in the Lecture Society of Hilberg, the psychologist and physicist Hermann Helmholtz in 1821 to 1894 had already pointed out that our perception by no means was restricted to the Euclidean relations in the physical world. So back then they were already studying this, and we'll get into the alley experiments that really pioneered this whole thing. How that shows the difference in how we perceive reality versus spatial versus visual, and what best describes the visual field, right? Is it Euclidean? Is it hyperbolic? That sort of thing. So there's a lot to consider there. We'll go over one more definition here from Wagner, and we'll be borrowing largely from this book, The Geometries of Visual Space, where he lays out a nice history and introduction to the subject. I thought I'd turn into a presentation here that we could go over the history of, all get familiar with it, see who the big players are here. The physical space, which is the primary concern of physicists in geometers, is defined by the reference to an object, physical measurements such as rulers and protractors. As a perceptual psychologist, I am interested in another sort of space, the visual space. Space concerns of where we concisely experience it, and studies those subjective measures, such as asking people through the numbers to estimate the perceived distances and angles and volumes. So
Is
basically,
that
how you perceive.
geometers? Is that a type of mathematician? What is a geometer? I've never heard of a geometer before.
Someone who measures the Earth.
Is it? It's a profession, a professional earth measurer.
Okay.
Physicist. So anyway, physical measurements, physically mapping something to the spatial field versus how you perceive something in the visual field. So if we were to look at the spatial field analysis of this, we would be talking about the actual heights of this building, the actual elevation of these rocks behind it, right? This ridge behind it, this deviation right here, these actual measurements of the topography, right? Like where it actually resides in relation to where we're at. So yeah, where an object physically resides in three-dimensional space in the spatial field is geometrically Euclidean. And actually, when we get into the celestial theodolite, we can prove that, or we can show evidence for that. We can falsify evidence against it.
There we go.
There we go. Sorry, got a little carried away. All right. But yeah, that's awesome, and we will be covering that because that's the important part. That's a big part of the celestial theodolite argument itself, is distinguishing spatial field versus the visual field, because people want to know, how come when I look through a theodolite, this mountain doesn't, it measures what the globe predicts. How does that work? Well, there's a deviation in the optical field, and it just so happens to be what they call the globe. And we can show that via starlight occlusion. But anyway, to continue on here, physical size and location relative to you. So if you were to map this out, all of this would be relative to some position here. You would be able to draw the actual three-dimensional relationship where these exist in three-dimensional reality. Now the visual field is defined by the overlapping of your left and right eye, where you have the binocular field of vision. Obviously, this whole 180 degrees is part of it, but this is how you would break it up into its subsections there. But this is where you perceive things. So this is not where an object necessarily physically is in reality. For example, if I'm looking over here at my desk and I see my phone is right here and I reach for it, the chances that I miss my phone because of some deviation are extremely low. Why is that? Well, I have a bunch of references to things that are close to me, for one, and that's helping me interpret distance and judge things and map it spatially. And locally to me, especially within reaching distance, that part of the visual field is actually best mapped as Euclidean. So the discrepancies and the deviations aren't going to be until you start looking at things that are further away, is kind of the distinction that I'm putting forward there. And actually all the optical theories that start with hyperbolic geometry, start with in the local field or in your local area, right, is going to be Euclidean. So that's the best way to describe what's directly immediate. Were you going to say something, Shane?
I was trying to figure out. I was trying to demonstrate myself by opening one eye and then the other, because this binocular vision would indicate that having two eyes gives you the proper depth perception. So therefore, if I close one eye and I still reach for the same phone, am I more likely to miss or less? That's what I was trying to figure out.
No, extremely important to point that out. That binocular vision part in the overlap there, that angle is what gives you that depth perception to make that judgment. Super important. So yeah, apparent size and location relative to you. And what we're going to find is that this is best geometrically expressed as non-Euclidean. And there's some hyperbolic uh, functions that are put forward to describe it. But there was a recent experimental measurement done in the early 2000s where they measured angular excess, which shows that the curvature can't be negative if that's true. So anyway, what I'm going to put forward is dynamic angular scaling, but get to that towards the end there. Anyway, just to kind of show what that looks like again from a different angle here. We have this overlap here creates your depth perception. Eyes there, as Shane was saying, if you close your left and right eye and reach for that phone, yeah, you're gonna immediately notice the discrepancy. All right, so in mainstream, it's widely accepted that the visual field is Euclidean. That's why when most people look through a theodolite and they see deviations and they go, well, that must be due to globe because optically, right? We see in Euclidean geometry when we get asked, shouldn't we see to China? Shouldn't we be able to look across the ocean and wave at people in England or whatever? Well, they think that they have unlimited perception, like unlimited information is coming at them like that, and they just have unlimited resolution, which
Well,
is
look,
preposterous.
when I look up at the stars, I'm actually looking backward in time through my atheist goggles at a thing that used to be a billion years ago, but is actually transmitting its little light BBs through infinite space infinitely. And now only through that and non-medium did it reach me, and I'm able to see light. So don't be silly, Alan.
Oh man, I totally forgot about um, like all that comes with the paradigm, where it's like,
Right.
dude, you're looking back in time when you look up at the sky.
But like that basic perspective is Euclidean translates into, well, I can see light from 100 million light years away. Those
Yeah,
two are directly correlative, right? Without
and
one, you don't have the other.
and it's actually the backbone of when they went to take measurements all over this place when they realized that they could use the relationship with trigonometric functions and stars, right? When they went to take the zenith measurements and none of them lined up where they expected them. So all of this goes into uh, how we perceive things versus where they actually are, and the story that we've been told about uh, the nature of where we live based on the relationship of how we perceive the stars.
Quite a trick.
Yeah, classic. All right, so there's a huge overlap here. If you were to teach people that these two fields are the same, it would be very confusing when they look horizontally through a theodolite and they see deviations that they can't explain because they would expect to measure the full elevation angle of something relative to them, with no optical compression or anything like that outside of refractive conditions, right? Like we're not even talking refraction right now. We're just talking strictly optical effects, how things scale in the distance relative to, because this is how they created the globe. This is why you can look through a theodolite and measure the globe and just make no assumptions and just assume Euclidean I'm making no assumptions other than Euclidean geometry. We strongly disagree that we see in visual that the visual field is Euclidean, and this is why, because if you don't contend on that point, then any measurement you see is going to deviate from that, and it can only be explained by physical Earth curvature. That would be the only way to interpret it. That's why they have that's why they have the illusion of such a strong position, because they can look through a theodolite and there's no claim to any optical effect other than refraction. And with enough refraction, right? Well, we know what they can do with that. So, all right. So, a quick refresher on Euclid's postulates. We're mainly concerned with the fifth one, and that is that parallel lines will never intersect. So, if the visual field is best described by Euclidean geometry, then railroad tracks optically should never converge in the distance. Now, suppose someone says, but what about when I get my special rectilinear, ultra flat, double wide reverse GoPro lens that has no curvature on it? It's actually concave, anti-parallel or whatever, right? What happens when I get that out and it shows that they don't converge? Well, that's fantastic, but we're not talking about what you can do with a special lens. We're talking about how you perceive reality with your own oculars, which is you know, if we see in Euclidean geometry, then railroad tracks shouldn't converge optically. Doesn't matter what you do when you put a special lens or whatever on them, right? That's insane. All right, so that's the primary postulate there, that parallel lines will never intersect. All right, so going over the history now of the visual field, we're going to talk about the alley experiment. So these are experiments that are done in a dark corridor, completely pitch black. And the participants are usually asked to light candles or arrange, things that are illuminated in parallel lines or in vertical parallel lines going outward in the dark. And what they find when they map them out, when they turn on the lights and map it out, they never map them out that would in parallel lines that would correspond to Euclidean geometry. They're always non-Euclidean. They actually they end up intersecting with the y-axis when they plot this out, which shows that it's non-Euclidean, like on the face of it. So the way that things are perceived versus where they actually are, there's a deviation at at different distances where these alley experiments are done. They're all done at different distances, and the participants are asked to do just different configurations of parallel lines. What they show when they map it out is that they're never parallel.
Wait, so you're saying they're trying to line up three luminous things? I don't know if it's candles or lights, right? In a straight line, once at each depth of field. So like closer, near, regular,
Yeah.
distant, and then far. Is that what they're doing?
Yeah, sometimes more. Sometimes it'll be like 8. Like it'll just be like just go out at try and keep them equidistant because they'll be given like specific instructions per thing. So, like one will be make them parallel and keep them equidistant to one another. Another one will be like put one here and then do it another one the furthest away that you can. And what they show is that there's always deviations. They always diverge. They're never parallel. They're not even close.
That's a good way to determine how you would see it, right? Because take away all sensory background, take away all things you can line up against, do it in the dark, and now based on what you're seeing, make it seem parallel, and that just shows you the depths of field at near and
Right.
close. I think it's a brilliant way to do it.
Right, and then when you give specific instructions too, that can like alter the results and stuff. So you have to, there's like specific wording and stuff even because the way that you perceive things, you can like visually alter or like you'll like know to reference something, and it'll give you like an advantage on judging the depth. So yeah, there's like a whole thing to it, but it's pretty interesting. So yeah, that was starting with Helmholtz in 1887, where he did the first alley experiment, and his measurements were showing that they were concave for the near points, and then convex for the as they got further away.
Wait, so the further away it got, the more Earth curve they found? I mean, they saw, or that it looked like, or whatever?
Yeah, essentially. And then in the small range, like where I was saying, it would be Euclidean. Oh, look, that's where it was the most parallel. No
Go
way,
figure.
no way, no way. All right, and then our boy Hillebrand came along and did the same thing, and he got the similar results. But his was doing it where he was telling them to maintain an equidistant relationship, and this is what he plotted out, like this deviation here.
Well, that looks mighty familiar.
Yeah, so his was there was two two sets of lights going outwards, right? Like on an X and Y axis, and it was to set the to keep them all parallel essentially, and this is the deviations that he plotted going, you were an observer at the center here. So again, outward, and then Blumenfeld did the same thing, but he did a larger distance and slightly different configurations and showed that the results get worse over distance, or the deviations are greater over distance essentially. But a thing to note is that when you plot these out, they're always within the optical corridor. That'll be important later when we get to Lundberg's theory of optics for hyperbolic geometry, because although his theory was falsified, if you apply the empirical measurements that were made later that show positive curvature, one of the things that does hold true is the predictions that can be made using hyperbolic geometry for specific distances and for specific distances. So continue on here. So there's the With-Mueller circle or torus that we'll get into. So this was started by Johann With. The 2D version started as a circle that showed like the angle that would be created all the way back to your retina based on your field of vision off of a circle. And later, a couple years later, Johannes Mueller made a 3D version, which is basically representing this equidistant relationship here. You can think of it as taking a sphere, or like a flat disc, intersecting it through your left and right eyes, and then rotating it 360 degrees. And then that would create this latitude and longitude system that you see through essentially, right? That's my
Right, it does like sweeping depths of field lines, right? If you were to sweep it through, it gives you varying depths of field at different lengths, which creates that grid, which is I think a good way to describe it. I personally love this because it looks like the most accurate way in which to describe the varying levels of depths of field that you'd have to apply varying geometries to, if what we're saying is correct.
Yep. So here's the angle relationship with respect to your with your depth perception and the angle that's going to be created going all the way back to your retina, and how you're going to be, is what you're perceiving in that near field or far field. And this is what I would put forward for like the causal mechanism of dynamic angular scaling, um, which is which I would say is best described as logarithmic, but we'll get to that at the end after we cover all the other geometries here. But yeah, so this is the Vith-Muller torus. This is another hyperbolic, equidistant geometric structure designed to describe optics. And the thing to note here is that all of these gentlemen had their own optical theories on curved visual space and the type of optical curvature that that we're experiencing. And some of them make the correct predictions for their respective experiments, but they're falsified by the other types of alley experiments. So it's just one. I just want to, um, keep it in the back of your mind that like just saying hyperbolic for visual space, because I thought for a while that that was like, there's this hyperbolic means hyperbolic, right? Well, there's different types of hyperbolic geometry, and then within that, there's actually they show that there's positive curvature measurements. So um, that's why I say that it's logarithmic now, because we can fit all of these measurements into an all-encompassing dynamic uh, system rather than trying to assert one specific type of geometry that only works in a specific instance and then act like that's the most bestest one, because that's kind of what's been done right now. And then, that's what these people were all trying to do, but couldn't do, because I don't think you really can. You're going to find that exact one-to-one relationship between the deviations for the spatial field and the visual field at distances. All right, so Carl Rudolf Lundberg in the early 1920s through the 1940s came up with a theory on optics using hyperbolic geometry, specifically using negative curvature as a constant to define his metric for space. So if we take this Mueller torus here and kind of project it out into a cone, this would be kind of what he's putting forward, how you see. And this is compatible with many of the alley experiments, but was shown to be incompatible with the measurements that we're going to cover here in a second. So to kind of talk about like this equidistant line relationship. So here we see these lines starting from the center are nice and equidistant from each other. As we get further away, there's a little, they get a little tighter, more compressed. But in the center here, things are pretty, they're Euclidean, right? So to speak. So if we were looking out, this would kind of be the rate of optical compression as you get further away from you. This would be how you would describe your near field. Now, when you get into things that are further away, that geometric relationship is going to change. And we can see that here as it gets more extreme a lot quicker. And as you get further out, it gets essentially flattened out. So that is the, due to the compression. So so keep in mind, like you see in both of these simultaneously, your eye, based on what you're focusing on, right? With our Vith-Muller here, based on what we're focusing on here and how far away it is, your eyes are constantly doing this at all times.
Right. So squinting, changing the aperture of your eyeball, lowering light, seeing further is changing the depth and varying the depth of field with which you're focusing, right?
Yep.
And that also makes everything right along the band, the diffraction band of your eye, right across the center, wherever you're staring at, that distorts all of that even more. That band gets bigger as your aperture gets smaller, as you're trying to look in at something far off in the distance. You actually will see less.
Nope, that's
along
just
the
sweet
horizon.
baby Earth curve.
Yeah. Yeah. It's amazing how much it adds up, like up to 3 miles. It's like the exact same almost.
Yeah. All right. This is taken from 2000. This is from a paper titled Direct Measurement of Curved Visual Space. In here, they used an arrow pointing at a sphere with an X on it. And here the participants were asked to, now she's super close here, but in the actual experiment, these were moved, out to the horizon. There weren't any visual references or cues. They were obstructed by the hay or whatever. So all they would really see was just this cube, this arrow, and they were trying to line it up with directly on the center of that crosshair on the sphere. And it was remote controlled here. They were judging from over here. They were lining up an arrow with a thing here. We can see the diagram right here. And what they measured from this was angular excess in the visual field. And they were relating that to
Wow.
Spherical geometry for optics.
Right. There's a table in here that says relationship of, let's see, angular excess to Gaussian curvature and you put a whole chart in about how you would derive Gaussian curvature based on the angular excess. That's insane.
Yeah. Yeah, so that was one of the things early on that Gauss figured out, because there was, when Euclid came out with his postulates, that was all the buzz, right? And everyone was kind of afraid to deviate from that. But Gauss came up with some hyperbolic geometry postulates and axioms, and then he was one of the first people to put forward that relationship, and part of that was based off of angular excess of spheres. And so what you could do is you could take the angular excess of a sphere that's measured on it, and it's directly proportional to the radius of the sphere.
Yep, it says it squeezes it right in there with the estimated standard error in the curvature. That's where it fits neatly.
Oh, no way. No way. You have to pull that up here when
Yep.
Yeah, from the paper here, we'll read a little bit about Gaussian curvature. This is in the Euclidean plane, the sum of a triangle is 180 degrees. Any deviation is called angular excess. This reveals the intrinsic curvature of space. The excess is proportional to the area of the triangle, and the excess per unit area is a measurement of the intrinsic curvature. Notice that the physical dimensions is 1 over length squared, thus the inverse of the square root of the absolute value, the specific angular excess, has the dimension of length. So the inverse square of the angular excess has a dimension of length to it. It's proportional to the radius that caused the angular excess to be measured in the first place. There's a direct geometric relationship there. And Gauss simply showed that it equals the radius of a sphere in the case of a spherical surface.
That's amazing. That's a super powerful slide right there.
Yeah, it's super powerful because it also illustrates that if, per se, you have a model in mind that has an exact geometric relationship that you're mapping positions of the stars to, and you need to take geometric measurements that have to comport to that model, well, you know exactly how much angular excess you need to get to show the correct relationship to your model.
Yeah, and if you were, say, to measure land triangles using your optics, I can see how something called spherical excess could be contrived right out of that angular excess beforehand. To be like, oh, look, we've measured the Earth, and here's the radius. How did I know the Earth's radius then?
Dude, it's so funny that you mentioned that, because check this out. They also point that out in this paper. They give 3 locations: Boston, Amsterdam, and Cape Town. Illustrates that if, per se, you have a model in mind that has an exact geometric relationship that you're mapping positions of the stars to, and you need to take geometric measurements that have to comport to that model, well, you know exactly how much angular excess you need to get to show the correct relationship to your model.
Yeah, and if you were, say, to measure land triangles using your optics, I can see how something called spherical excess could be contrived right out of that angular excess beforehand. To be like, oh, look, we've measured the Earth, and here's the radius. How did I know the Earth's radius then?
Dude, it's so funny that you mentioned that, because check this out. They also point that out in this paper. They give 3 locations: Boston, Amsterdam, and Cape Town. And they give the angular excess over that area, which would be the only way that you could, describe Earth curvature over these vast distances. Because check this out. Notice that the specific curvature is small. In the instance, the angular excess of an equilateral triangle with sides of 1 kilometer is only 0.002 seconds of arc. Locally, the Earth is quite flat. Dude, so even if we lived on a sphere, like that would be true. Like, but that's crazy, right? Like that. Yeah. You
He's
can't
trying to find curvature over 1 kilometer.
No, you can't be done. So only referencing adding up these large distances by summing up triangles that you're measuring at the maximum that you could see at the horizon, going to horizon, creating triangles, doing arc of the parallel type stuff is the only way that you could get angular.
Which, don't you know, is just what they did.
Which leads into what I was putting forward for how we perceive things optically, which is through a logarithmic scale, where we have linear portions where things would be best described as Euclidean, where we have things that get into a hyperbolic function where they get more compressed, and then we have the logarithmic scale where things get ultra compressed at the extreme far field. Do you have anything to add on how we see things, Shane?
Is that a leading question or something I forgot to add? Crap.
Well, no. So we went over 3 specific types of geometry that were put forward. Well, actually, I kind of breezed over them, but Each person had their own type of geometry to describe the visual field, which is the deviation from the spatial field. And they were one was spherical geometry, and the other two were hyperbolic geometry, and one was using uh, constant negative curvature, so that it keeps things equidistant. So that's like utilizing the Withmuller idea, right? So Lundberg was using that equidistant Withmuller relationship, and then so when you do the different alley experiments based off of distance and do you want your parallel? Do you want them to be parallel at a great distance, or do you want them to be short, intermediate, equidistant relationship things? There's these different models. Either hold true or falsify by these relationships. But if you unite them under one umbrella, one logarithmic scale, perhaps.
Then
What are
you
your
get an
thoughts on that?
azimuthal grid of vision, right? Yeah, you get a spherical limit of vision put forth in front of you, based on an equidistant direction in every direction. Look at that. Look how the scale applies at the horizon versus how it applies directly over you versus where it would be linear, hyperbolic, or non-Euclidean. That's perfect. That's a perfect representation.
Nice. All right. So how do we measure the distance, the difference between the spatial field and the visual field? Well, we have the old celestial theody. That is where you use the timing in which a star gets occluded to match up with a specific calculated angular relationship based off of your distance to a mountain and its physical elevation peak relative to your elevation. That difference will give you a raw angle that you can use to reference when a star will be occluded at the peak of that mountain. And if the timing matches up at your location where you can no longer see the star at the time that same angle matches up for that star to be there geometrically, with respect to its true position, with respect to its true almanac position, then geometrically the spatial field is Euclidean. And the only way that would work out is if this triangle over all this distance had no curvature to it, because the timing in which this star will get occluded corresponds to a specific physical elevation.
So this is, I don't want to complicate things, but this is a great proof of this. So if we were to say that in reality, the stars were flat, right? And they were just a flat above a flat baseline forever, but the limit of our vision and the visual field cause us to see what is flat in a hemisphere, right? You can't see forever. So if it extends linearly above you, you would see it appear to rise and set as it comes and go. So if our perspective is putting in, say, the geometrical curvature limit and things are in fact flat, then what we would expect is things to be occluded physically that at times which align with those flat angles in perpetuity for every observation. That's what you would expect if in fact the stars were flat, but our perspective sees them in a hemisphere around us.
The sky dome is the visible hemisphere of the sky above the horizon in all directions.
I thought I made that up. Wait a second. Did I write that book?
Wait, is this from a solar panel manual from the 60s? Talking about your azimuthal. I like sky dome. Azimuthal grid sounds too professional. Sounds like something a flat earther made up. Sounds like something a flat earther made up. I'm a sky domer now, guys. We see in a sky dome. And look, so anyway, they're talking about the relationship between where the sun physically is versus where you optically see it and how it arcs across the sky in your, what's that word I'm looking for? Sky dome. As it goes, the sky dome is the visible hemisphere of the sky above the horizon in all directions. How many directions is that? That one?
Omnidirectional, yeah.
Oh, huh. So real quick, I want to show a great curved visual space, visual dome here. My boy Taboo Conspiracy. If you haven't watched Taboo's channel lately, wake up.
There's amazing work.
It's time to watch Taboo. This one right here. A quick shout out to Man of Stone because he does a nice introduction to a video that Stone did on measuring the sun set shadows. But real quick here, I wanted to go over Ben's anti-crepuscular shadow.
No video again.
Check this out. Like this cloud that the sun
Can you guys hear this on your end or nah?
is hiding
You don't necessarily need to hear it, but I'll narrate it for you guys since you guys can't hear it.
behind has broke through. Looks like a spotlight. And then it carries over. Oh.
I don't hear much narrating.
All right. So the sun is being blocked by a cloud and it's creating a shadow that's going over my head. And as I'm taking the camera and panning it over, we're looking at this shadow reaching its maximum dimensions of divergence at my zenith, meaning directly above my dome ski. at 90 degrees. And then as I continue to look behind me, I see it start to diverge into the horizon. Or I'm sorry, reconverge into the horizon on the opposite side, 180 degrees away from me.
So in reality, that's just a really long perpendicular linear shadow across the sky. But because it extends past the limit of your vision, you're actually, your limit of your perspective is converging it behind you as if you had a spherical limit of vision. That's crazy. That's
As
a
if-
crazy example.
As if you could see behind you. Like it creates the necessary components to interpret reality behind you. She's not. That's crazy, dude.
Beastible says, don't forget about the penny. I thought we had a prop.
Oh, the penny. All right. So this was in regards to Euclidean geometry and curved visual space. So one of the examples that was given was the penny looks pretty Euclidean right now, right? It's very circular, but if we turn it, it becomes elliptical, and it's non-Euclidean. So that was the example there.
Oh, how about that?
That was well worth the penny. Thank you, Beast. Massive budget. All right. All right, so he's got a couple more examples of these awesome shadows that will play out, and a quick recap on the Mount Rainier situation. I think that was Mount Rainier with the upward shadow, and how, you know, our argument has been this is a matter of perspective, right? This is how it looks if you see in a, what's the word I'm looking for, in a sky dome. What happens if you see in a sky dome? All right. So here we go.
Is that not the coolest thing? It's like I'm under a giant canopy.
As I explained then, this triangular shadow from the cloud disproves the globe propagator's claim that this triangular shadow from Mount Rainier is a supposed upward shadow being cast on clouds above the mountain. The globe claim is entirely wrong and frankly a bit childish. The triangular shape is only a matter of perspective and has nothing to do with the shape of the mountain. Only the top part of Mount Rainier is casting a shadow and is being cast on clouds below the peak. The triangular shape is simply perspective from a lower vantage point. How can I say that with certainty? Well, first, the supposed upward shadow has never been filmed from the top of the mountain, ever. Second, the triangular shadow shape cast from the cloud.
We're not
clearly matches the shadow
narrating.
from Mount Rainier.
We're just seeing the.
Shoot, sorry. So Ben's going over the fact that the shadows have never been observed going upwards from an observer on top of the mountain, which would be completely necessary if the sun was geometrically underneath the mountain. Otherwise, it would be a matter of perspective if, per se, an observer stood on top of the mountain and saw the shadow converging at the horizon, like he went over here in these examples here. So this is a perspective thing, right? This is what this shows the whole time. There was one other example here. Sorry, I got kind of sidetracked. One new example of the shadow.
That's what the shadow really looks like. Then how am I seeing an anti-crepuscular shadow from the ground? That's crazy. Or is my perspective putting everything in a sky dome?
I'm gonna go with sky dome since my solar panels only work when I account for sky domage. It doesn't say anything about Earth curvature. It's like talks about how I perceive the sun in my sky dome. That's weird.
Which was filmed August 5th, 2024 at 8.
All right, here
Wouldn't we see this like every tall mountain, like every time there's a cloud somewhat close to it, if it wasn't the mountain above the clouds? Like, shouldn't we see this all the time? If they're saying, oh, it's just shining upwards at it, well, why doesn't this happen all the time then?
Oh,
Well,
not only should it happen all the time, there should be an eastward and westward sweeping shadow that's like a hard defined geometric, arc
Yeah.
across the sky of darkness that's just 15 degree per hour, taking away your light.
right,
all
that
your-
curved shadow of everything should sweep across the sky every night as an acid from the bottom of the earth, right?
You know what doesn't happen? That, and we have to argue 17 different iterations of nautical twilight based off of elevation angles to the sun beneath my feet refracted up. Like,
7
dude-
layers of gradation twilight makes sense for a globe for that argument, okay?
Yeah. Like, dude, that's why you should definitely check out I have a link here for Mana Stone's video. Sun. Yeah, you should definitely check out his new sun measurement. A couple thoughts about. Oh yeah, he does a live prezi here on Clubhouse. Shout out to the Flat Earth gang over there. Yeah, the sun setting above the horizon, classic. And then obviously Taboo's video here.
Impossible on a globe, just so everyone's clear. Sun cannot set above the horizon for any reason. So
Yeah. So let's see here. So I'll let Taboo play out his thing here. So he filmed this.
And it died down before I started recording. But my video makes an excellent point because notice where the sun is. This video, which was filmed August 5th, 2024 at 8:35 p.m., was taken only 4
Same
minutes
effect.
before
Beautiful.
sunset. The sun appears to be lower than the clouds. You can't even see it. Under the globe, the sun would have to
Decrepuscular shadows. Is that what we're calling those?
So if the sun is lower than these clouds on the glob, geometrically, then these clouds should be underlit. But you notice how no one has ever seen this before? And so what he was showing 4 minutes ago, or a couple seconds ago, was the sun 4 minutes after it supposedly set. Globe.
to be at an angle lower than the clouds, but we know that's not true because only the tips of the clouds are casting shadows.
And so he points out that only the tips of the clouds are casting shadows. So, in other words, the sun can't be below the clouds to do that. Otherwise, it would look like showed in the previous slide here.
Friend Robert, who now lives in the Philippines, just sent me
Right.
these.
So all aspects of that, we perceive a linear world with, our visual field or whatever. Can't help but appear to perceive it that way.
Yeah. Yep. That's awesome, dude. Shout out to Ben. Thanks for that awesome curved visual space shadow video. It's like
Taboo Conspiracy. What is he on? 3 now, I think?
no, he's on like 4 or 5.
Jeez, oh Pete, yeah, he's had his channel taken down so many times.
Every time it builds my respect for him, though.
Mm-hmm. Badge of honor.
This comes right back to it.
Dude, shout out to Gauss for figuring out curvature and then burying it with angular excess and then pretending spherical excess proves stuff. Shout out to Gauss. Gaussian coefficient, refraction coefficient, Ben did some work.
He's gouged out of his mind. All right, let's see if there are any questions. Chat here.
Dude, I noticed that your highlighting got way better.
Yeah.
Only
Like
the
that?
important stuff highlighted. It was crazy. Yeah, I was
You
like
like that?
professional and everything.
Thanks. I realized Canva is if I'm gonna use Canva, I might as well use Canva, right?
Love it. Excellent
All right.
presentation.
Not seeing any questions in the chat, so everyone absorbed all of the information. Everyone now knows the difference between the visual field and the spatial field. One is Euclidean, one is non-Euclidean.
Did we link the paper for everyone to do their homework and follow along at home?
Ooh, great question. I'll put an Obsidian link in the description, actually, all the citations. But actually, if you go through the presentation itself, I'll put a link here. All the citations are in the slides. All right. Zach, what do you got coming up this week, sir?
I will be hanging out over at Iron Realm Media for Monday, Wednesday, and Friday morning at 5 a.m. And then Thursday night, we'll have a Glowbuster Tech. We had a really good one on shadows and like looking at an object and being able to tell if it's an actual sphere or not. That was actually a pretty cool one. If I could.
Didn't Karen make that, I think? That one?
Yeah.
I love that one.
That one. And then I was showing how you can totally get rid of a shadow, like surgical lights. They use 2 Fresnel lenses and they put it in front of a light source. And when you do that, something really crazy happens. Like as soon as you get about 4 inches away from whatever you're looking at, there is no shadow anymore. It totally just disappears the shadow. And with one Fresnel lens, you can make the shadow much smaller than the actual object. Something you can't do without a Fresnel lens. Usually a shadow is the same size as the object or much bigger, depending on how close it is to the light source. Yeah, actually, I'll just pull up the Glowbuster episode. I just wanted to show you, well, no, I'll just pull up the video. This one video I shared about using a hemispherical lens, because we may have a hemispherical lens above our heads, some sort of lens like that, lensing effect at least going on. And it's really crazy what you can do with light and these lenses and make it look like an object is an actual sphere. So let me share this real quick. Okay, sorry about the, my first 100 or so videos were done on a phone.
What?
Here's a laser
I thought we were friends and I respected you. I didn't know that. I'm sorry, Zach.
So as you can see, it's not a spherical image. It's more of like a square. It's kind of even bows out the other way. These are those cheap lasers you can buy from like Etsy or something like that. One of those types of places. You can get them for like $5, and they come with this little filter on it, so you can project a bunch of different lights instead of just the one. Now, what's really cool is when I pull this hemispherical lens out here. Okay, come on. I'm screwing the thing on. Oh, I need to hide that. There we go. Okay, here you go. So as you can see it projected on there, doesn't look spherical, right? I mean, maybe the center part because of the light source was so dominant, but watch what happens when you put it through a lens.
That looked like a very good representation of the field right there. That green grid spread out there, it looks like an excellent representation of the visual field as played out as they have in that paper. Matched it almost exactly.
So or a shape that isn't a sphere, when shined through a hemispherical lens like that, look at that. I can rotate it on any axis at any degree. This is why I say I really don't know what the sun is. Like the original shape of the sun even. I don't know. It could be a square and coming through the atmosphere, you know, could make it look like this.
Yeah,
But it was a really, really good episode. It was a fun one. And we had Kyle, a video that he did, we covered on it, on shadows, and how when you move them in front of another object, you know, like when you cast a sphere shadow onto a sphere, it doesn't look like the eclipse at all. But when you cast a sphere shadow onto a flat circle, it kind of looks exactly the same. And just little things like that, yeah. And then Karen B's one with the 4 different objects. Can you guess which one's a sphere? Yeah.
Classic Karen
But yeah.
B.
I love that one.
Mm-hmm.
Playing Guess the Sphere with Karen B.
But yeah, optically, I mean, there's so many tricks that nature can play on us. I mean, when you have a living lens all around us, you know, no matter which direction you're looking, nature can, you know, distort the image and fool you.
Yep, and then evil men can come along and be like, "Ooh, you know what serves my evil purpose of dystopian future and totalitarian control? If I were to convince you that it's actually a globe, don't ask why or how; it'll all equal out later."
All right, real quick, we got a couple of super chats that came in. One from Express. So she says, "Love you guys."
She's
Thank you
the
very
best.
much. Which is great. Daniel McLaughlin comes in, says, "Wait, Euclidean and non-Euclidean? There's a difference?" Yes. One implies parallel lines will never intersect. The other one implies that they will. Pretty.
Alters the parallel postulate.
The old parallel posty, they call it. You go to Google and type parallel posty.
Just like that. Yeah.
Yep. Grok will know exactly what you're talking about. They're like, "Oh, did you mean Euclid and the boys and his 58 postulates?" Shane, we got coming up this week. I heard you were doing a ether cosmology roundtable on a bunch of celestial stuff that nobody could explain except for you.
Are we? When you say me, you mean us, right? I thought that was a joint venture.
Oh, it is.
But yeah,
a joint,
I think
is a
we're
joint
doing
venture.
a roundtable on all of Jaren's problems with the flat Earth.
Yep, we're going to be going over the old list.
We
Taking a gander.
We should definitely ask Kyle to come over. He's been doing a little 1v1 series about Jaren's objections and making videos on each one.
Oh, yeah?
I bet he'd love that.
His help would be very appreciated on this one.
Yeah,
I think.
I bet he'd love
Nice.
that too. Yeah, Kyle's a good guy.
Doing good work on this precisely. So yeah, if I'm on my own and Space Audits is bailing, I tag in Kyle.
Well, I was segueing you to tell what we have coming up because it's a joint operation. But yeah, I'll be there, obviously.
Yep. That way, is that this Tuesday? We're doing that? Is that or next Tuesday?
What is this Tuesday? Is this the last Tuesday of the month?
And next Tuesday's the first. Yeah, okay.
Yep, we are doing it Tuesday.
We'll be trying to address all of Jaren's objections for leaving Flat Earth. That's going to be Tuesday on Ether Cause.
All right, and then next week on Globebusters, we'll be doing a special Thanks Bob segment. We'll be going over the ether properties, sidereal rotation, what it means to measure sidereal rotation. Does it mean that the thing you're on is spinning? How doth thy tell? Someone asked, right? So we're going to be going over the history of ether properties. Be next week. All right. See you guys
Nice.
on Tuesday.
Thanks, everyone.
Oh, wait, before we go, one more from Daniel. Ball has no spin. But ball go spin.
He said, but ball go spin, bro. Man, you can't even read a super chat, right?
but ball go spin. Totally forgot about that argument, had not considered it. All right.
Great. The new GoDaddy Arrow has AI marketing tools to help small businesses easily